Hello and welcome back to this series of lectures on calculus. In this lecture, I will present some key aspects of the theory behind the slopes of polar curves. Now, as we've seen in the last couple of lectures, we can define the position of a point in the plane by using polar coordinates, and then we can use that system to define polar functions and the corresponding polar curves. As this picture here indicates, this, as you may remember, this is a type of polar curve that we may consider something that rotates around the origin. So polar coordinates and polar functions may be appropriate here. And of course, if I can pick a point there, and I can consider the idea of a tangent line. I can consider the idea of the slope of that curve. And I can do that, of course, in any other point like that one or any other one that you may care to consider to analyze. However, if we give the function in polar coordinates as a polar function, then we have to be careful how we compute that slope. It's not going to be dr by d theta, because that's just going to tell us how fast r changes with respect to theta. For the slope, that's not what we want. What we want is still to compute how fast y changes with respect to x. Okay? So let's look at this thing algebraically and see what we can do in order to solve this problem. First of all, we start from the fact that we can write any polar function whatsoever in parametric form as a parametric curve. Why is that? Well, remember, a polar function is written in the form r is some function of theta. By the way, here is a new notation. I'm going to use a new convention, which is very, very common. And it is, if I'm using a polar function, I will write r as the dependent variable, as well as r being the name of the function of theta, if it is a function of theta. Sort of like writing y equals y of x. Okay? So if I have a polar function like that, then I can use my change of coordinates formula. Remember, we said we can go from polar to Cartesian. Well, I can use those two equations and say that if I have the polar function r equals function of theta, then I can this can be represented parametrically by the function x equal r of theta times cosine theta, and y equals r of theta times sine theta. So I'm using those change of coordinates form, or if you want, just plain geometry. And so because of that, now I know how to compute slopes, because you may remember that we know how to compute slopes for parametric curves. So we can just use that in order to figure out what the slope of a polar function is. The formula that we come up from this in general are not easy to work with. So doing a first derivative analysis, for instance, is not going to be that easy. And don't start panicking. I'm not going to ask you for any difficult questions about that. However, we're going to especially be looking at this formula in one particular situation. However, let's try and work out that formula and see what that formula looks like, even though we know it's probably going to become complicated. So let's see. The slope formula for a parametric curve is that dy by dx is going to be equal to dy by d theta divided by dx by d theta. This is the traditional formula that we've used to find the slope of a parametric curve. Well, let's see, what does it turn out in this case? Well, it's a fraction. On the top, we have to compute the derivative of the y coordinate. So the derivative of this function here as a function of theta. Now remember, here both r and sine theta are functions of theta, so we have to use the product rule. As we do that, we end up with r prime sine theta, derivative of the first, plus r cosine theta, which is the derivative of the second. Same thing in the denominator. We have to take the derivative of x with respect to theta, again using the product rule. So we come up with r cosine theta minus r sine theta, which is of course the derivative of cosine. So this is the formula. And again, told you this was not going to be an easy formula. So it is a formula which can become fairly complicated. Notice that this already looks quite messy, and we don't even know what r is, right? If r is in fact a specific function with a formula of its own, we'll have to place that formula in place of r. And then we'll have to compute its derivative and place in for r prime, and you can imagine what a mess this creates. So once again, in general, this is a bit of a problem. Okay, so the first derivative analysis can become very complicated. Just setting the numerator and the denominator equal to 0 respectively by itself is going to be giving us a headache. Okay, however, there is a bright side to that. Okay, remember, in polar coordinates, The extrema, which is what we're looking for in terms of dy and by dx, the derivative gives us the slope, but it also gives us the extrema. Those are not really that important. It's not that important, although we will be playing a little bit with it. It's not that important to find out what is the highest or the lowest point. We want to find out what happens with relation to the pole. We want to find out how this thing turns around the pole. That's really the key issue for these polar curves and polar coordinates and so on. So let's find out what happens when we're trying to find out what the slope becomes when a polar curve goes actually through the pole. Okay. So here is the formula on top, and let's consider this polar function. Let's say this polar function goes through the pole, as you can see there. Okay. So when does a polar curve goes through the pole? When r becomes 0, because of course the polar coordinates of the pole are 0 and whatever number you want for theta. So if we put r equals 0 in the formula for the slope, what that does, it has the effect of canceling those terms with r cosine theta and r sine theta, and leaves us just with r prime sine theta divided by r prime cosine theta. Well, this can be simplified further. The r primes cancel, and sine theta over cosine theta simply becomes tangent theta. Okay, so the formula has become easier, fine and dandy, that's good already, but there is more to it. What have we really found? We have found the following. Notice again, this curve is going to be scanned radially, right? So we pick a value for theta that hits the curve somewhere. Then we pick another value for theta, hits the curve somewhere else. Picks another value for theta, another point on the curve, and so on. Now, what happens when, in fact, the value of theta ends up hitting the pole? Well, what happens is that the radius, the line that joins the pole to the curve, ends up being pretty much the tangent line. Okay, well, let's analyze this formula that we found. What we're saying is that the slope of this tangent line is going to be equal to the trigonometric tangent of the angle theta for which we actually hit the pole. But remember, tangent of theta is actually the slope, right? It's the rise over run, opposite over adjacent. So that means that the tangent line at the pole at r of theta, so once the curve goes through the pole, forms an angle of exactly theta. So in other words, a polar curve has to go through the pole, forming an angle which has to be equal to the value of theta that generates it. Now, again, we're talking theory here. The words I'm saying might be a little bit confusing. When we go to class, we're going to be looking, or when we look at some examples, we're going to see how that plays out in practice. But this is something quite useful. In fact, it is something that helps a lot in graphing some of these curves. And remember, the whole point of polar coordinates is to be able to graph certain curves that have a rotating pattern around the origin. So this particular thing will give us a lot of help when we're trying to graph some of these functions and help us get those graphs and get the properties of those graphs in a much easier way.